What's up everyone? Today we're going to be going over word break. Now the input is going to be a string and a list of strings, and the output needs to be true or false, whether we can make this original string using a combination of these guys. Now there's a couple ways to solve it, but I'll be going over the dynamic programming approach, and I'll be going over the recursive, then memoized, then the tabular DP bottom-up approach. So first I'm going to explain the logic behind it and draw out the recursive tree, calculate the time complexity, and then we'll get into the code. So what's the intuition behind this problem? Well, first we want to know whether we can get this, so we check if the code exists in here. It doesn't. So what we can try doing is taking away one letter at a time, right? And then see if that one letter exists in the dictionary, then we can recursively check for the smaller subproblem. So let's take code. So C exists in here, right? So word break of code, what we first do is take away one letter, right? And we first check if it exists. If it does, then we can recursively check for ODE. Now when we're doing word break of ODE, what we do is take away one letter and recursively check for DE. Well, O is not in here, so what can we do? We can take away two letters. If 2 is not there, we can take away 3 letters. I mean, not in, for ODE, we can take away 3 letters and look for ODE. So OD and word break of E. Well, OD exists in here, so we can look for the word break of E. E actually is another one in here, so this expression is going to return true, and this expression is going to be true because of this one. This one will say false, but if either one of this is true, this guy can say true, and he can return to the original problem, and we can get back true. So let's see what the tree for this is going to look like. So word break code, we can have C and word break of code, or we can have CO and word break of DE, and COD and word break of E, or we can just have the original one and word break of empty. So the word break of an empty string is the base case, and it's going to be true. So how can we break this one down? This can be O and word break of DE. This can be OD and word break of E, and ODE and word break of E. This can be broken down D and word break of E. This can be DE and word break of empty. This is going to come out to be E and word break of empty. This is going to be D and word break of E, and this is going to be another one. This is going to be DE and word break of empty. This can be E and word break of empty. This one is going to be E and word break of empty. So we use this recursive tree to calculate two things. One, we calculate the runtime complexity, and two, we learn how we can use memoization, which is storing the values of the recursive expression where we can reuse it again. So what I mean by that is this word break of DE is actually being done twice here. So if we calculate the input, okay, this also needs to go here. So E and word break of empty, yeah, keep it consistent. So if we calculate this one, we can reuse that over here, and that's how memoization works. It saves us computation time. Now for calculating the runtime complexity, let's see every single recursive stack where we have a non-empty string. So this is the original one of length n, another one, another one, another one. Okay, so how many is that? 1, 2, 3, 4, 5, 6, 7, 8. So for a string of length 4, we're going to have 8. So the number is 4. And, oh, n is 4, yeah, n is 4. The number is 8. For a length 3, it's 1, 2, 3, 4. So 3 is 4. So for 2, it's going to be 1, 2. 2 is 2. 2 is 2. And 1 is going to be 1. So how do we get this? This is 2 power 3, this is 2 power 2, this is 2 power 1, and this is 2 power 0. If you notice, n minus 1 is 3, 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0. So the runtime complexity is O of 2 power n minus 1, or we can say 2 power n. That is how we calculate the runtime complexity. So now let's see how this translates into code. If we're given a say boolean word break, set string s and a list of strings, say list. First we put all the list of strings into a set because it has fast lookup time. Then we populate our set, or string L through list set dot add L, and then we recursively call a helper function. I call it DFS, pass in the string s and the set. So the core logic is going to be in this helper method. Say it's called DFS. In recursive functions, the first thing we should always take care of is the base case. And like I said, if we have an empty string, it's going to be true. Otherwise, we get into the core logic where we break away one piece at a time. For int I is equal to 1, I is less than equal to s dot length I plus plus, and if the set contains s dot substring from 0 to I, then we're going to check recursively the rest of the substring. So s dot substring I till the end of it, and pass in the set recursively. So if this is true, then we return true. This is the left hand of the branch, and this is the right hand of the branch. Then we return true. If none of our breakdowns work, then we return false. So that's the plain recursive version. Let's see how we memoize this. To memoize, we use a data structure, in this case a hash map, which the key is a string, a substring, and the value is true or false of the value of the recursive calculation. So now we can say map string boolean map. Now, if our map already contains the value of a substring we've already calculated, we return it immediately in the beginning of the recursive function. So if a map contains key s, return map.get s. Otherwise, we go back and we check here. Now, where do we populate the map? We populate the map right before we're about to return a true or false. So if we're going to return a true for a substring of this, then what we say is map dot put s dot substring of I, s dot length, and then we put in what we're going to return. Just say true. Else we come here. If we're about to return false, just put it in the map. And that completes our memoization. Now let's look into the tabular approach. So DP, dynamic programming, can actually, the solution for, say, a length, a DP of a string of, say, 4, it's going to be represented as a DAG dependency. So it can be true if any of these is true. So DP of 3 or DP of 2, DP of 0. And these itself are going to have different dependencies. So what we do is we calculate from the bottom up. So first we do DP of 0, then we do DP of 1 based on that, then DP of 2 based on what we have already. Now, let's define what DP is. DP of I is true if the word break of substring 0 to I is true. So if we want to know the DP of length n, then say DP of n, this is going to be based on DP of n minus 1, DP of n minus 2, so on and so forth, DP of 0. So how do we do this? Well, if we're going to if we want to know the answer for a length of 4, what we start with is a length of 0, a length of 1, length of 2. So we're going to go C is going to be length 1, CO is going to be length 2, COD is going to be length 3, CODE is going to be length 4. So to get this, we use the previous ones. I'll actually update the DP array when I'm writing the code now. So let's say we have a Boolean word break, string S, and a list of strings. I already defined what DP of I is going to be. So let me create the Boolean array for that. It's going to be new Boolean of length n plus 1, where n is the length of S, so S length of plus 1. So we want to return, we want to get this guy for the whole string. So let me actually write down one, two, three, 4. So the code is this. For int length of 1, length is going to be calculated until the string full length, and then length plus plus. And then we're going to do it this way. So for a length of 1, we're going to move the pointer from 0 to here. Then when length is 2, we're going to move the pointer from 0 to 1. Then when length is 3, I is going to go from 0, 1, 2. And length is 4, I is going to go from 0, 1, 2, 3. Now, the code for that is going to be like this. Int I is equal to 0, I is less than length, and then I is plus plus. Now this is the core one. If dp of, so what we're trying to do is to calculate the dp of I. So if dp of, dp of length. We're trying to calculate the dp of length. So if dp of I, and if dp of I is true, and the list contains s dot substring I to s dot length, then we can make dp of length true. And we can break, because all we care about is if the length is a true or false. Even if the length is true in one particular way, that's all we care about. So that ends that, and then we have to return dp of n. So let's see what this looks like. Now this is 0, 1, 2, 3, 4. For that word like code, the base case is always going to be true, so we need to write that as well. So I'll say dp of 0 is true. Now when length is 1, I is 0, and we say substring from dp of 0 is true, right? And does list contain substring 0 to okay, this actually is not s dot length. This has to be just the length itself, yeah. This is going to be the length itself. So because we're looking at C first, and C is contained in there, so this is going to be true. Then we break. Now we look at CO, right? When we're looking at CO, is CO, when we're looking at dp of 2, when we're looking for dp of 2, we check it with dp of 0 and CO. CO doesn't exist. Then we check it with dp of 1, and we check with O. And that's false. So this is going to be false. Then when we get to, actually I can use a different marker for this. When we get to dp of 3, we check dp of 0, and we see COD is in here. It's not. And COD, that's false. And then we check dp of 1, and we look for OD. OD is in here, right? OD can be found from here, and dp of 1, which is this, is true. So we update this to be true, and then we break. Now, when we're back at dp of 4, let's see how we can get that. dp of 4 depends on dp of 0 and code. And code. Code is not there. What about dp of 1 and ODE? It's not there. dp of 2 and DE is not there. What about dp of 3? Right? dp of 3 and E. dp of 3 is true, and E is true. So this is going to be true, and that's how we know that the original input is going to be true. So if you like the video, let me know, and thank you for watching.